Good afternoon, everyone. This is our pre-launch news conference for NASA's Multispheric Multiscale mission, or MMS as we know it. And here to talk about the launch and the mission that's coming up is Jeffrey Yoder, Deputy Associate Administrator for the NASA Science Mission Directorate in Washington. Omar Baez, the NASA Launch Manager during the countdown from the Kennedy Space Center. Vernon Thorpe, Program Manager for NASA Missions from the United Launch Alliance in Centennial, Colorado. Craig Tooley, the NASA MMS Project Manager from the Goddard Space Flight Center in Greenbelt, Maryland. Jim Birch, the Principal Investigator from the Southwest Research Institute in San Antonio, Texas. And Clay Flynn, the Launch Weather Officer from the 45th Weather Squadron. And we'll begin first with opening remarks from Jeffrey Yoder. Jeff?
Thank you, George. This week is an exciting week for NASA, our partners, contractors, as we prepare to launch 4 spacecraft to help solve the mysteries of how magnetic fields around the Earth connect and disconnect. And you'll hear more about that in our science briefing tomorrow. But MMS is a challenging mission, and if it's possible because of the hard work and dedication of this great team, and it would be difficult for me to mention everybody by name who was involved, but I would like to reference or to say thanks to our certainly the NASA team, our international partners, our contractors, universities, and our launch providers for making this happen today. I would also want to spend time just to say thank you to the families that allowed your loved ones to really spend this last 5+ years working on this amazing mission. You were part of the success of getting us to this point also. So I'd like to say thank you to the families that sacrificed your time. George?
Thank you, Jeff. And now to Omar Baez, who is our NASA Launch Manager in the countdown tomorrow night. Omar?
Thank you, George. And good afternoon, everyone, and thank you for attending today's brief. I am again fortunate to be here representing the men and women of the NASA Launch Services Program at Kennedy Space Center and our partners, United Launch Alliance, and our customer, Goddard Space Flight Center. These folks have been dedicated to analyzing, fabricating, assembling, preparing, and testing the Atlas V and the 4 MMS spacecraft, which is set for launch this Thursday at 10:44 p.m. This will be the 53rd flight of the Atlas V launch vehicle. This will be the 4th time this 421 configuration is used. And that is the 400 series rocket with 2 solid rocket motors. And we are using an extended payload fairing for it. We'll have a short video, if you could roll that. I'm going to show you how this is 2 or 3 months process is done in a minute. That's the booster arriving on the Foss Mariner from Decatur, Alabama, and it's on its way to the ASOC facility. This is the booster on the way up to the pad as it's being erected. It's powered by the RD-180 engine using kerosene and liquid oxygen. As I said before, it's got 2 solid rocket motors, and those are being erected there. And the top of the stage is the Centaur, powered by the Aerojet Rocketdyne RL-10A. And that's the Centaur there. That stage is powered by hydrogen and liquid oxygen. And that will thrust the 4 MMS spacecraft, which you see there in the payload fairing, to its intended orbit. The 4 MMS spacecraft were encapsulated within that 4-meter fairing 2 weeks ago in Astrotech, and they were brought over to the Cape. They were stacked on Friday, February the 29th, and over that weekend and through the week we've been testing and doing a liveness test on the spacecraft and doing the integrated systems test to make sure that all the electrical paths through the spacecraft and the launch vehicle are working correctly. Last Friday, we completed our flight readiness review. Yesterday, we did our mission dress rehearsal, and this morning we successfully held the NASA launch readiness review. We plan to roll the vehicle out of the vertical integration facility tomorrow at 10 in the morning. We will connect the electrical, fluid, and pneumatic and environmental control system up to the rocket and the P-van. We will then load kerosene into the Atlas V booster. The following day, just after 3 p.m., this is Thursday, the team will power up the Atlas and the Centaur, perform the flight control checks. We will get into our facility chill down. Our launch management team should be in place by about 6 p.m. And at 7:44, we will have our first hold at T-minus 2 hours. This is a 30-minute hold. At the conclusion of the poll, we'll give concurrence to proceed with cryogenic tanking. Approximately 2 hours later, we will be done with cryogenic tanking, and we will enter our 30-minute hold at T-minus 4 minutes, and that'll occur roughly at 8:10 p.m. At 10:30, I will poll the team for concurrence to enter terminal count and release the hold at T-minus 4 minutes. And after confirmation that the spacecraft is configured for launch at about 4.5 minutes, I will inform the ULA launch director that NASA is go for launch. The expected T0 tomorrow is at 10:44 p.m., and we have 30 minutes of launch window. Back to you, George.
All right, thank you, Omar. And to Vernon Thorpe, the program manager for NASA missions from United Launch Alliance. Vern?
Hey, thank you, George. United Launch Alliance is honored to be here again with all of our NASA customers just 2 days before the launch of the MMS mission. Our ULA team actually started working with NASA to integrate MMS onto an Atlas V almost 6 years ago, back in 2009. That's a little bit longer than we usually work on these missions. This mission had an unusually long integration period, which allowed us to work with the spacecraft team to define interfaces and environments early, which allowed for some requirements, stability, and definition of environments early, which ended up resulting in lower risk for this very complex mission. After defining the requirements early, we were able to ramp down the integration effort for a while, and then we returned to more of a normal schedule a couple of years ago when we got into the normal 2 years before launch. MMS will be the final Atlas mission to be launched on our original NASA Launch Services contract, also known as the NLS-1 contract. That's the contract managed by our NASA LSP customer, and we do have quite a few other NASA missions that are being integrated for flight in the future. Those are all being integrated under the newer NLS-2 contract. So this one will close out NLS-1. We began building the Atlas V for this MMS mission in Decatur, Alabama, about 2 years ago. We started the technical integration work a few years before that, as I mentioned, and we've analyzed and developed solutions for many unique requirements, both physical interface requirements and operational requirements associated with this mission, and we've tested and verified those solutions. The ULA, LSP, and Goddard teams have worked very hard to get to this point. It's been a tremendous team effort, as always, and we're all looking forward to a great launch on Thursday night. This will be ULA's third launch of the year. It'll be the 94th total launch since ULA was formed back in 2006, 94 launches in just over 8 years. We have a very busy manifest in 2015 with 13 launches planned, and 10 of those will actually fly from here at Cape Canaveral. MMS will launch on an Atlas V 421. The 421 configuration has that 4-meter diameter payload fairing that you saw a little earlier, along with 2 Aerojet Rocketdyne solid rocket boosters attached to the Atlas first stage. The Atlas booster for this mission will be powered by the RD Amros RD-180 engine, and the Centaur upper stage will be powered by an Aerojet Rocketdyne RL-10A engine. And to give you a preview of what you'll see when the rocket flies on Thursday night, I'd like to show a short video. Can we cue that up? So here's the vehicle lifting off. When we light the core engine along with the 2 SRBs, we'll lift off with about 1.5 million pounds of total thrust. On this configuration vehicle, the next major event that you'll see is burnout of the SRBs. Those will burn out about 99 seconds into flight. We'll hang on to them for about another half a minute so that when we jettison them, we'll be safely downrange. There you see that happening. The first stage propellant will be used up after about 4 minutes. At that point, we'll command booster engine cutoff like you see there. 6 seconds later, we'll separate from the Centaur upper stage. We spend a few seconds preparing for the first of 2 engine burns, and then we'll light the engine. That first engine burn will last just over 9 minutes. We'll jettison the payload fairing very early in that engine burn, as you see there. And then at the conclusion of that first engine burn, we'll enter a parking orbit coast that lasts almost an hour. It's a 59-minute parking orbit coast. At that point, we'll be in position for the second engine burn. That second burn will last 5 minutes and 41 seconds, and that will put us into the orbit we want to be for spacecraft separation. Now, we have a very unique separation sequence for this mission because of those 4 spacecraft. We'll separate the first one 14 minutes after the second burn. That will give us time to orient to the spacecraft desired attitude and to stabilize the vehicle. And then we will separate at 5-minute intervals. So the time from the first separation to the 4th separation will be 15 minutes. And what we want to do is we want to minimize disturbances on the upper stage between those separations. So for about 20 minutes, starting a few minutes before that first separation, we'll actually lock up the propellant tank vents, and we'll do everything else we can to keep that vehicle as stable and rock solid as we possibly can, so that we just have minimal disturbances between separations. Prior to each separation, we'll spin the vehicle up to about 3 RPM, and then in between separations, we'll spin back down and hold the vehicle stable. This will actually be NASA's 12th mission to launch on an Atlas V rocket. And as you know, Atlas and Deltas have been delivering NASA science missions and other important payloads to orbit for decades. We're always focused relentlessly on delivering those critical capabilities to orbit, and right now we're focused on our NASA customer and on the MMS mission. And I'd like to say thank you again to all of our mission partners who helped us get to this point, and the entire ULA team looks forward to a successful launch on Thursday. And with that, I'll hand it back to you, George.
All right. Thanks, Fern. Now to Craig Tooley, the NASA MMS project manager from Goddard Space Flight Center. Craig?
Good afternoon. In a moment, I'll pick up where Vern left off, describing how the mission unfolds. But before I do that, I'd like to just say a few words about really as we near the culmination of well over 5 years of what is the development of probably one of the most challenging missions that both Goddard Space Flight Center as well as Southwest Research Center has ever done. As you can see from what you've seen already, we have built 4 large, identical, very sensitive spinning spacecraft that we will fly in formation. So, here 2 days before launch, I'm honored to have helped in concert with Jim Birch lead this team, which at times was over 500 people building this mission, which we're about to launch. That team has been made up of a variety of institutions, but namely Goddard Space Flight Center, Southwest Research Center, University of New Hampshire, and a whole plethora of other both domestic and international partners. If we could show the next video, so here we're going to have a little bit of overlap. You can see here we are about leading up to the separation sequence. The Centaur is putting out our initial. You see the fairing separation, which we sense on board. We are spun up to 3 RPM here, and we'll begin to separate. Now, separation is actually separated by about 5 minutes, so we've sped up a little bit here so this press conference isn't too long. But each MMS spacecraft separates and in turn activates and then deactivates its transponder so we can talk to it. You see here the first of our booms deploying. These are the magnetometer booms, 5 meters each, that unfold, the shortest of our booms, all while we're spinning at 3 RPM. Now you'll see an illustration of the deployment of what we call our spin plane double probe booms. These are 60 meters on a side, 4 wire booms, which we deploy to sense electric fields while we're spinning, obviously spinning to keep them taut. And then finally, we're going to see here the deployment of the axial booms, the one that go out in our spin direction, which go out 15 meters at both ends and carry receiving elements to sense fields at their ends, leaving us with 4 spinning spacecraft with the booms spread out that actually have a footprint about the size of a baseball field. And you see here in this view, you can actually see the other MMS as illustrating the formation. Although we fly these as close as 10 kilometers together, we will adjust that formation as we fly. And as Jim Birch will talk about which regions of space we actually do our science in, we are continually fine-tuning this three-dimensional formation so that we can capture magnetic reconnection. It's best to think of this mission as an in situ flying laboratory, not really a remote sensing, but it is operated throughout its 2-year mission continuously by scientists on the ground, essentially using our own magnetosphere as a laboratory. Now, in the next video, if we could roll that, we'll just get a little insight into how we fly. There you see the MMS observatories or spacecraft represented by those 4 dots flying in formation. They make up a tetrahedron, so we can get a 3-dimensional capture of magnetic reconnection events as close as 10 kilometers together. You can see the magnetic fields represented there. Essentially, when you fly something in formation, you end up needing to fly 4 different but very similar orbits continuously, and we have to then fine-tune those orbits to maintain that formation. We'll fly them as close as 10 kilometers together. We'll fly them with an accuracy of 100 meters while we do that, and as often as every 2 weeks we will do propulsive maneuvers. We carry about 400 kilograms of hydrazine rocket fuel on board each one to do those maneuvers with. Now, before I turn it over to Jim Birch to tell you a little bit more about the science, we'll move backwards in time a little bit, and we'll run a little clip that shows just a little sample of what happened almost 4 months ago when we arrived, as we began our journey from arrival here at the launch site to finally being encapsulated and on the rocket. So if we could show the next video. So here you can see we actually shipped the MMS spacecraft to Astrotech, our payload processing facility, 2 at a time. We reused a transporter, so we made 2 trips. And you can see in this, you can see us actually unwrapping the first of the stack of 2. In that picture, you saw 2 MMS observatories. Here's the arrival of the next 2. You'll see them lifted off. These observatories are about each 4 feet tall, about 12 feet across their octagonal cross section. Of course, that's how big they are before we've deployed those booms I spoke of. Cleanliness is very important to us, as is magnetic cleanliness, as was electrostatic. These are extremely clean spacecraft, lest we measure our own noise in terms of magnetics, electric fields and such. So we worked very hard to make these extremely clean spacecraft and having no magnetic field of their own, no electric charge buildup of their own. And as this video moves on, you can see actually here we're seeing when we stack them into the stack of 4 that make up the stack configuration that we launched that you saw earlier. In this picture, you see covers on the solar arrays, and you see protective debris shields that we've wrapped over the top, but essentially this is how we began to look. And there you finally see a beautiful picture of the stack of 4 MMS spacecraft flanked by the Atlas fairing. You can see the solar arrays, and around the top perimeter you're catching a glimpse of the some of the 25 instruments. There's 100 instruments total on this mission that we built. And now we're seeing the actual act of encapsulation as they move the Atlas fairing around us. And then finally, that evening, we moved it out to the launch site. This is actually the rollout when the encapsulated payload moved out to the vertical integration facility for hoisting atop the Atlas rocket the next day. That brings us almost to where we are today. Now, after this, I'm gonna hand it back to George.
All right. Thank you, Greg. And we'll learn a little bit now about the science from Jim Birch, who was the principal investigator for the MMS mission from the Southwest Research Institute. Jim?
Well, thank you, George, and good afternoon, everybody. Magnetic fields are continuously being generated and destroyed throughout the universe. The generation part's pretty well understood as a result of circulating currents and conducting fluids that are in planets are conducting gases in the outer parts of the sun and stars. This magnetic field generation is known as dynamo action. The destruction part results from magnetic reconnection, which occurs when magnetic fields in adjacent regions of space interconnect. In the process, magnetic energy is destroyed and heat and kinetic energy are released. But exactly how magnetic energy is destroyed in a reconnection event is completely unknown. Because of its explosive nature, magnetic reconnection is often described as a magnetic explosion in space. Reconnection is important to us as the engine that drives space weather and the main disruptor that is frustrating our attempts to harness nuclear fusion with magnetic containment devices. The MMS mission will conduct a definitive experiment in space that will finally allow us to understand how magnetic reconnection works. And we have a video that introduces the topic But first you'll see a region surrounding a black hole at the center of our galaxy. And we see magnetic loops that reconnect at their base. This is sometimes called loop-type reconnection. The same type of loop reconnection occurs on the sun, as we see here. The magnetic fields on the sun form these very dynamic arcades and loops, and the energy stored in these structures can release, creating explosive solar flares and coronal mass ejections, as we see here. This reconnection was first proposed in 1948 by a graduate student who noticed that when sunspots with the same magnetic polarity came together, nothing happened, but when the two sunspots had opposite polarity, solar flares would result. Now here we see what happens when the coronal mass ejection reaches the Earth. You have magnetic reconnection happening both on the day side and the night side of the Earth, as we see here. And this creates the aurora, the lights in the upper atmosphere. But this also causes charged particles to be accelerated to very high energies, creating a hazard to space travelers and spacecraft, and even disrupting ground-based power grids. Next slide. The fundamental question is why and how does magnetic reconnection take place? The answer is in one sense simple, but in another sense complex and mysterious. The simple part is that adjacent magnetic fields pointing in opposite directions at the top part and bottom part of that figure tend to annihilate each other, releasing their magnetic energy, heating charged particles in the surrounding environment. In this process, the magnetic fields are torn apart and reattached to their neighbors. The mysterious part is what goes inside that box labeled diffusion region. With MMS, we will be able to probe the diffusion region for the first time with measurements down to the smallest scale of the plasma, the electron scale, to solve this mystery. Now, the next video shows the targets of our mission. This is a diagram of the Earth's magnetosphere, the solar wind coming in from the left. There are two boxes there. That's where reconnection occurs. Inside these boxes, the phenomena we want to study exists. So this is a computer simulation. This particular plot is of electron currents. And you can see the dynamic nature, why we need 4 spacecraft to probe particles and electric and magnetic fields to much higher sensitivity and resolution than have ever been done before to work this out. The next slide shows how we access these two regions of interest. The next video is our orbit in red. So we launch on the night side. The orbit precesses through the day side, skims the magnetopause. We're varying the separation between the spacecraft in that tetrahedron as we go. The second time we pass through the magnetopause, here we hold at the optimum separation, somewhere between 10 and 160 kilometers. Now we double our apogee, sweep through the night side, adjusting our separation between spacecraft between 10 and 400 kilometers. So once we've done this, after this 2 years, we will have performed a definitive experiment on magnetic reconnection. We have to make particle measurements 100 times faster than the previous record because that's the electron scale. Previous missions have only been able to study the ion scale or the fluid scale. And so the previous missions have only been able to know what happens outside that box, not what happens inside it. And even the computer simulations are just guides because as we know, the proton mass is 1,836 times the electron mass. The largest computers we have can only handle a ratio of 100. And it would be a long time before computers big enough to do this would be able to. So MMS is the only way we can solve this mystery, and we look forward to doing it. Thank you, George.
Thank you, Jim. Now I'll look at the weather forecast for Thursday night from Clay Flynn, the launch weather officer from the 45th Weather Squadron, Department of the Air Force. Clay?
Thank you very much, George. If you could bring up the satellite picture, please. If you look out into the western Gulf of Mexico, you'll note quite a bit of cloud cover, and the cloud cover extends into the southeast states. That's associated really with a lower pressure in the western Gulf that will slowly migrate to the east, as well as associated frontal boundaries there in the southeast states. Looking off to the east, you'll note that we have pretty fair weather, not many clouds out to the east of the Florida Peninsula. And that's associated with an upper level ridge that will tend to retard that eastward motion of that system that you see in the western Gulf. So as we approach launch day on Thursday, we should see the system migrate slowly towards the east and be steered to the north. So that ridge out to the east will actually tend to deflect that that system that you see, the extensive cloud cover that you see there to the north and east. So on launch day, would expect to see the bulk of that to the north and to the west. Looking into MLP roll tomorrow, we'll have southerly winds. We'll likely have some coastal showers. The winds are from the south-southeast. We should be gusting in the mid-teens at about 230 feet about the time we roll tomorrow, with a few isolated coastal showers, not looking like it would pose any concern really for a roll to pad tomorrow. And again, the system stays out to the west and to the north. As we move into launch day on Thursday night, again, the system would remain, the system that you saw in the Gulf would remain out to the north and west. So the bulk of the cloud cover and the showers up that way. However, we do increase in moisture in the upper levels. So that would be a potential concern for thick cloud roll. It looks like the moisture, the clouds would dip down to near about with a minus 20. And if we get clouds between 0 and minus 20 that have greater than 4,500 feet thick, associated with them, then that's a thick cloud roll concern. So we'd have to monitor that. That's one of the concerns for launch day Thursday evening. Likewise, in the lower levels, in the lower 10 to 12,000 feet of the atmosphere, our winds go southeasterly. And essentially what that aids in is bringing in coastal showers. Coastal showers typically are favored during the nocturnal hours, so with a late night launch, we'd start to see showers enhance a bit, and with the southeast flow trying to bring those showers on shore. So that would be the second concern as well, cumulus cloud roll. So those are the two principal concerns for Thursday evening: thick clouds streaming in from the west, and then cumulus clouds streaming in from the southeast. So our winds are actually in opposite directions. They're low-level winds from the southeast, upper-level winds from the west. About a 30% chance of violation on Thursday evening. We'd be looking for scattered clouds at about 3,000 feet. A broken deck of clouds at about 25,000 feet, and the clouds look to be pretty thick above that, but the base of those clouds about 25,000 feet, right about where the minus 20 is, so we'd have to monitor that. Good visibility. Our winds should be southeasterly, and these are at a couple hundred feet, gusting to about 20 knots, and that's below the liftoff constraint, so it doesn't look like winds would be an issue for Thursday evening. Should we be on the pad for a 24-hour delay? Some deterioration in the sense that we have an increasing moisture in the mid and upper levels, which would tend to make a greater threat, greater cloud cover and greater threat for thick cloud roll violations. So 40% chance of violation at this time for an attempt on Friday evening, should we be on the pad Friday evening. Again, we'd be looking for scattered at 3,000 feet. More clouds in the mid-level, so a broken deck at about 18,000 feet, and then an upper-level deck about 25 to 30,000 feet. Winds a little more south-southeasterly, gusting in the upper teens with a 40% chance of violation. Again, that would principally be cumulus cloud and thick cloud. And that's all I have, George.
All right, thank you, Clay. And we're ready now to take questions. We'll start first with media here in the room, and if we have any questions on social media, we'll be able to take those as well. So we'll start here with Marcia. Please give your name and affiliation when you get the mic.
Marcia Dunn, Associated Press, with two spacecraft questions and a big question, probably for Mr. Twilley or Dr. Birch. You mentioned 10 kilometers is the closest you would like the spacecraft. What's the farthest that they can be to work efficiently? Do you need all four, or could you get by with 3 or fewer? And what will be the practical applications of the knowledge gained from all of this?
Why don't I'll start the answer, and then Jim Birch can pick it up in a little more detail. But first, the easiest one is we need 4 spacecraft, because in order to get 3 dimensions, we essentially need 4 points in space. 3 will make a sheet of paper. So that's in order to capture and do measurements in 3 dimensions. That's why we need 3. It is true that if one were to fail late in the mission or something, we can still do significant science with only 3, but certainly not meet our main objective. So we need all 4. 10 kilometers to almost 200 kilometers, and then later in the second half of the mission, we may fly as far apart as 400 kilometers. But because we don't understand magnetic reconnection well enough, that's why we will actually use the first part of the mission, and Jim could talk a little bit more about this, to essentially optimize that separation distance in order to, when we start seeing magnetic reconnection events. So you want to elaborate a little bit, Jim?
Right. Well, 10 kilometers is the electron scale and the plasma scale when the densities are high, like on the day side of the Earth. We go to the night side, the densities are lower. We can have a larger separation. We want to go out to the 400 to also get the ion scale. Even though that's been done before, like for the by the European cluster mission, we want to connect the two. We want to connect the ion scale to the electron scale physics. Now, as far as practical applications, this mission is part of the Solar Terrestrial Probes program. There's another program in NASA heliophysics, directors here, Jeff Newmark, and that's called Living with the Star. And that's more of the applied. It's not really applied, but it's research that's more of, say, for example, forecasting space weather would be a goal of Living with the Star. It wouldn't be a goal of Solar Terrestrial Probes. The goal there is fundamental research. And the fundamental research we do, however, since I mentioned earlier, the magnetic reconnection is the engine that drives space weather. So it causes the solar flares, the coronal mass ejections, the geomagnetic storms, the aurora, the high energy particles, both at the Earth and the ones produced from the sun. All of that is produced by magnetic reconnection. So everything to do with space weather starts with reconnection. So I would say if we can understand it, and our goal isn't to predict space weather, but we would understand it much better than now. And I mentioned only briefly about tokamaks, the magnetic confinement fusion program, and that's been a program that's been frustrating the last couple of decades, because you confine a plasma in a donut-shaped magnetic field, build up the temperature to start getting fusion, and temperatures always drop. They call these sawtooth crashes. What causes those? Magnetic reconnection. So as we learn how reconnection works, and we work closely with the people at Princeton Plasma Physics Lab who do these experiments, we think it could enlighten them on how best to do better.
All right, Ken?
Hi, excuse me. Hi, Ken Kramer for America Space and Universe today. I have two questions for Craig and Jim Birch. For Craig, you've talked a couple of times about the magnetic environment for these spacecraft is incredibly low. I was wondering if this has application in other science experiments and payloads that you guys can apply in the future. And for Jim Birch, I guess you've been thinking about this for a long time. Your goal definitely is to solve this problem. So can you talk a little bit of reconnection of how did you why did you choose the instruments that you chose for this experiment? Maybe you can give us a little preview of the science briefing, please. Thanks.
For this mission, we needed very advanced instruments. As I mentioned, the speed of measurement of the particles, a factor of 100 times faster than had been done before. And so whenever you form a team like this, of course, you want to get the best groups that have the best instruments, have experience flying these before. And, of course, there are competing teams, and so you lose some people and you gain some different people. So it's a very interesting process that you go through, and then you compete. But all of these instruments were beyond the state of the art. And as we got into it, we had to take some different approaches. Craig was talking about University of New Hampshire. They took on a much bigger job than we had planned in the beginning. They designed and built all of those spin plane double probes, and it's a very impressive activity going from not having done it before to doing the most advanced system we've seen. Also, I wanted to mention an instrument that we have on there that I actually designed. That's why I don't talk about it too much, but it's a mass spectrometer, an ion mass spectrometer working in KeV range. All the previous missions have not been able to measure heavy ions like oxygen from the ionosphere as they flow into the reconnection region because of contamination by solar wind protons, which have very high fluxes. So you needed a way to turn those fluxes down but not affect the oxygen fluxes. That never had been done before, and we have an instrument called the Hot Plasma Composition Analyzer that does that. And so for example, if oxygen coming in there cuts down the reconnection rate, that might help the people in the laboratory as well. We don't know. It could go the other way, but we'll know.
And I can follow up on your first part of your question. And in fact, one of the reasons this mission was built at Goddard, we did this in-house, was because of the challenges of making this so magnetically and electrostatically clean. And this is applicable in almost any mission that follows on that would have magnetometers or electric field sensors. And indeed, we are between 100 in some cases to 1,000 times cleaner or have lower residual magnetic fields and lower levels of actual charge buildup on our spacecraft than a typical spacecraft. And essentially, we have now set the standard, at least at Goddard Space Flight Center, for not only what one could achieve, but the practical methodologies of how do you cancel out all of your magnetic fields from all of your electrical equipment that has running currents? How do you control all of your construction materials, and all of your surface treatments so you don't build up. We only build up 4 volts across the whole spacecraft. And a typical spacecraft that doesn't concern itself with this, and sometimes it doesn't matter, can have 10 to 20 kilovolts of charge built up on its surface. Indeed, if you had gone up on the launch, as ULA integrated the rocket and put us on, you would have found we essentially had magnetic police at every station, and we had people there with magnetometers and sensors. No tool gets close to the MMS spacecraft that's not either magnetic, non-magnetic, or gets degaussed. And this has been going on for years. We degauss everything. We don't build with magnetic materials. So I think we've proven we can do this, and we've really set the standard for when one needs to do it again. We know how to do it.
Calico Field with Space.com. I have a question for Clay and then one for Craig and Jim. Can you estimate how visible the rocket will be, what the visibility conditions will be on Thursday night, how far away people might be able to see it? And then Craig and Jim, just wondering if there's any kind of a limit on when MMS needs to be launched to get into its ideal orbit, any kind of a window that you need to meet?
I don't expect a lot of low clouds, so really I would expect typically what you could see on a typical launch, so certainly from Orlando or even west of there. I think we'd probably lose visibility, although you'll see the light go through the clouds, but once it gets up to about 25,000 feet or so, I think we'll start to see lose the visibility of the clouds, so you probably might not see the SRB separate, which is typically pretty good or pretty fun to watch. But generally speaking, I think we'll lose it after about 25,000 feet. Because I think we will have broken and then maybe even broken to overcast clouds as it goes downrange.
To answer your question about the launch window, we can launch any day. We have about a 30-minute window, and it varies just a little bit depending on as we move through the calendar. It gets a teeny bit shorter as days move on, but we can launch any day of the year, essentially. So from a spacecraft achieving our orbits and such, we don't have a constraint. We just have a 30-minute window each day throughout the calendar year. And we actually worked quite hard to establish, it was a lot of work for the science team to make sure that we could fine-tune our requirements. Earlier in the program, we had some preferred seasons. But as it got difficult to make sure we secured the earliest launch date, we refined that so that we essentially opened MMS up to launch any day of the year. We're going to launch in 2 days or 3 days, but we could go any day of the year.
Daryl?
Daryl Nail with Fox 35 out of Orlando. For Jim, once you're able to solve the magnetic reconnection, do you know where that takes you from there?
Well, we think we know how to solve this problem because we're going to measure down at the smallest scale at the highest time resolution that's needed to get down to this electron scale. So we think we'll solve it. There won't be a need for another mission. But however, every mission I've been involved in, there have always been surprises, new mysteries, new things to come up that you want to study or need to study. So I can't count that out. But we think we have an optimum experiment on reconnection.
And its application to nuclear fusion, you touched on that briefly. Can you explain where they would take that data?
Well, they're very interested in our mission because in a plasma tank, you can only make very rudimentary measurements like temperature, density. That's about it because it's pretty small. You can't fit this whole spacecraft in one of those tanks. So they'd like to know what's going on in there, causing reconnection that's defeating their confinement of plasma up to these high temperatures, 100 million degrees in the electrons, but they can't do it. But we can do it in space. So they're just very interested in scaling what we're doing to what they need to do.
All right, we have a question right down here.
Yes, historical imagery, Mark Gotch from Canada. Can you tell me, this being the last of these series of missions, absorbing this important data of the magnetosphere, the fold-out 40-foot booms, would these be the same type of booms that were previously on the other satellites launched? And would this enhance what you're going to gather in terms of this information on this launch?
Yes, these actually, well, not 40 feet. Each one is 60 meters out. So, okay, so that's more like 200 feet in each direction. But that's not a record. I was PI of another mission called Image, where we had 500-foot antennas like that, and it was tall as a new Empire State Building, I believe. You took both directions. So, but we were doing something different. We were transmitting waves from those antennas and looking for reflections. For what we need to do here, the 60 meters is is good. I think it's typical. It may not be the longest. It's longer than what they have on cluster. But the main thing is we have that third axis. The cluster mission only had 2-axis electric fields. And the only thing they could do was assume the electric field along the magnetic field, that one component was 0, because theoretically it should be 0. But in a reconnection region, it's not 0. That's exactly what happens. You get an electric field component along the magnetic field. So to do a 2D electric field measurement for a reconnection is not going to tell you anything. And so we do have these three, and as far as the actual mechanism, I think it's a very advanced mechanism that has been developed by UNH. In fact, the PI for that sitting in the back, Roy Tarbert, and we've got a lot of confidence in it. But it's much better in that it's 3D, really.
Right, we have a question here in the front.
Callie McPherson, University of New Hampshire. In your opinion, will the success of MMS lead to any greater roles for any of the academic space science centers in any future satellite missions?
I would hope so. You know, you have to, it's very interesting how you sell missions. There's a really cool program in NASA called the Explorer program. So every few years you got an opportunity and you can propose anything you want. And that was what the image program was, and that's very satisfying. And that's the field is really taking some real leaps by the Explorer program. But these are small, like 1/5 the size of MMS. For the big missions, you have to sell it through the National Academy. This means committees of hundreds and hundreds of people, filter it all out, and finally, here's the priorities. And in 2003, MMS was the #1 priority in solar and space physics for the National Academy. And if you say that, NASA will move on it. The very next year, or that same year actually, we were writing our proposal. So that's what they will always say. The Congress and NASA will say that decadal survey is the Bible. So if you can get a mission in there, and then you can propose and win it, okay, that's a long process. So I'm certainly hoping that that process can continue. It should, but I can't tell you what the missions are going to be.
I follow up on your question a little more practically. I would hope the success of this fosters what you said, because the scope and the quality of the engineering that we saw come out, especially of University of New Hampshire. I mean, the challenge that was taken on was not small, build a single instrument. It was, they solved some very large engineering problems and managed a whole suite of fields instruments. I mean, it was very impressive. So hopefully that too would gain some traction as people look.
All right, any further questions? All right, and we do not have any, Darryl, you got a follow-up.
What was the total cost of this program from the beginning to the end?
So the total cost, including launch vehicle and everything, is around $1.1 billion.
And okay, one more follow-up here.
Hi, Ken Kramer for America Space again. For Vern Thorpe, you mentioned there's a very long time for prep work. Can you describe why it took so long to prepare this and integrate these satellites?
I think we could have done it on a more nominal timeline, which for a NASA mission would probably be around 3 years, 2.5 to 3 years. But we had the opportunity NASA had the opportunity to select the launch vehicle 6 years in advance. And whenever you can do that, it's nice for the spacecraft team to know what they're going to fly on. They can begin working right away to understand in detail the exact environments that they're going to have to design to. They don't have to do enveloping analyses, covering all the possible launch vehicles out there. So I think there was a unique confluence of events that the opportunity presented itself. NASA took advantage of it, and as a result, we were able to define requirements early, which always benefits the spacecraft program. Oftentimes, when a launch vehicle gets involved, the spacecraft is already at its critical design review. And if we run into a requirements incompatibility, even a minor one, it costs a lot more to solve that. We were able to avoid all that on MMS. But if we had needed to do it in 3 years, we could have.
I'm wondering specifically about this satellite, like the magnetic environment. You use an extended payload fairing. I know it's very cramped inside the payload fairing because of the size of the satellite. So did that contribute to it, or can you talk about those issues?
That wasn't really a problem. It is true that this stack of satellites fills up the cylindrical section of our longest 4-meter payload fairing, but it stays within the allowable envelope. We have an envelope defined within that fairing that, as long as the spacecraft stays within it, it's fine. It accounts for all the the relative motion that takes place during flight. So that really wasn't an issue. Probably some of the most challenging requirements on this mission were the magnetic cleanliness that we talked about, but Goddard was in charge of that, so it really was not hard for us to comply with that. And because the 4 spacecraft are stacked, we had some unique physical interfaces. The electrical umbilicals and purge lines, for example, come in from the side rather than coming up from the bottom like they traditionally do when you fly a single spacecraft. So we have these draped lanyards that extend across from the side of the payload fairing and interface with the side of the spacecraft. We've done that before on other missions as well, but it's a little unusual. I think this is the first time we've done it for 4 spacecraft at the same time.
And I'd follow on with that, we do use the whole fairing, but it's not because we almost outgrew it. It's really that we optimized to exploit the fairing we have. Being that we have fixed solar arrays, the physical size of our spacecraft, equates to our power margin and such, both the height and the width. So essentially, we designed to optimize the 4-meter fairing once it was established and use every bit of it to our advantage.
All right, seeing no other questions, and we have no phone-in questions or online. So a couple of programming notes. First of all, the rollout is tomorrow morning at 10 o'clock, and we will be replaying some of that on NASA television. And then also tomorrow afternoon at 1 o'clock will be a completely unabridged mission science briefing on MMS. So invite you to come back and tune in then for a even broader picture of the MMS science objectives. So for further information, if you would like to go online, you can go to www.nasa.gov/MMS. Thank you very much.